Welcome to the SAFECode e-learning course on Cross-Site Request Forgery, or CSRF. The objectives of this course are to help you understand CSRF as a pattern of attack, become aware of hotspots in your application where you should be particularly concerned about CSRF, and lastly, provide upfront strategies to prevent CSRF in your design and implementation. The primary intended audiences for this course are architects, developers, and testers of web applications or other software deploying web technologies. Development managers will also benefit from this material. Because the pattern a tester would use to look for and protect against CSRF is the same as what an architect or developer must use during advanced planning, a separate testing course is not required, as there are no techniques specifically for testers. First, we will illustrate what cross-site request forgery is, why it's bad, and how it's accomplished. We'll then point out the prerequisites leading to CSRF vulnerabilities and examine solutions for effectively preventing CSRF. We'll also provide helpful implementation hints and warn you of common pitfalls. In order to explain the potential impact of CSRF, let's back up and ask a more basic question. What malicious actions could you take if you were able to remotely control someone else's web browser? You could make the browser send requests to any reachable web server without requiring any action by the user, and if done cleverly, the initiated traffic would be unnoticeable to the user. Just sending requests seems harmless. However, as you use another person's browser, you also share any existing session context with that person, since session cookies automatically append to all requests leaving the browser. Hence, if the user has previously established a session with a web server, the server will accept your additional requests as if the user intentionally sent them. Depending on the application, you may be able to invoke wire transfers, orders at an online shop, or post spam emails and fake social network entries, all on behalf and without the consent of the actual user. The CSRF attack pattern enables an attacker to gain remote control of someone else's browser. The slide shown illustrates the basic steps of the attack. First, the attacker must install a malicious web page on a carrier server. The attacker must design the malicious web page in such a way that, when loaded in a browser, it will send subsequent requests to the target server. These are the forged requests mentioned on the previous slide. Later, we'll explain how the malicious page may trigger a forged request. Next, the attacker needs to lure potential victims to the malicious page. A successful attack requires that the victim opening the malicious web page has previously logged in to the target server. Otherwise, a forged request would be sent without a valid session cookie. Assume that the victim has initiated an authenticated session with the target server prior to loading the malicious web page. When processing the malicious web page, the browser sends the forged requests to the target server. If the forged requests fit into the current session context, the target server will accept and process them as intended by the attacker. Thus, the attacker achieves his goal. In this real-world example of a CSRF attack, a single GET request could change the firewall settings of a specific Linksys router. Sending the GET request during a valid administrative web session is the only prerequisite for this attack. By embedding this request in a web forum or blog post discussing administration issues for this router type, attackers were able to trick router administrators into unintentionally loading the malicious page. If an administrator read the malicious web page with an authenticated web-based configuration interface session open in the same browser, the page would disable the router's firewall functionality. This would allow the attacker access to the router's web interface and possibly the local network. In this example, the CSRF attack not only allows the attacker to misuse the victim's session, it also makes sending requests to the router's web interface, typically unreachable from outside the local network, possible. Many potential opportunities exist to embed GET requests in a web page. HTML image and iframe tags make the browser load images or frames from a given URL. Attackers can then embed the forged request in the corresponding URL parameter. A URL can also be included as a refresh parameter in the web page meta tags. Using JavaScript, It's possible to do more than just trigger an arbitrary GET sequence. JavaScript also allows sending POST requests by auto-submitting hidden forms provided by the attacker. The slide shows two HTML code examples. Whether sending a GET or POST request, the browser automatically includes any existing session cookies and HTTP authorizations for the given URL. It is important to denote that JavaScript, in general, cannot read or process any data returned in response to forged requests. In other words, when a script allows the browser fetch some data, the data does not return as a variable that the script can read. This is due to the same origin policy. Therefore, it's impossible for the attacker to access the response data or redirect it elsewhere so he can read it. That's why the primary goal of CSRF is to cause a stage change on the server. The response to the forged request is useless to the attacker, and he needs some other way to determine if the CSRF attack was successful. Now that we know how automatic GET and POST requests can be embedded in a web page, we'll now discuss some additional prerequisites for a successful CSRF attack. First, the attacker must lure potential victims to this web page. A common tactic is sending phishing mails with links to the malicious page. Another is to use a web page that will be highly ranked by popular search engines, which a potential victim will see when looking for information about the target application. Next, the forged requests must fit into the victim session context to gain acceptance by the target application. The attacker must be able to create a valid request without knowing the specific session context. As we'll see later, CSRF prevention techniques aim at this aspect by making requests unpredictable for the attacker. Finally, the forged request must be sent in the context of the existing authenticated session. Therefore, the browser must add the session ID to the request. This will be the case if the session ID is stored in a cookie and if using the same browser instance to connect to the carrier and target servers. Though transmitting session IDs as URL parameters instead of using session cookies may prevent CSRF, we do not recommend this due to other security concerns. While instructing highly privileged users, such as administrators, to connect to your web application with a dedicated browser instance can be an effective organization countermeasure, it's difficult to ensure that users will adhere to this rule. Protecting a web application against CSRF attacks can be broken down to the problem of distinguishing forged requests from benign requests. Benign requests result from the actual usage of the web page by the authenticated user. These requests can result from a user clicking on a link or from embedded JavaScript refreshing page content in the background. Solutions to this classification issue rely on a shared secret included in the benign requests sent between the web application and a legitimate user's web browser. The attacker must not be able to guess or retrieve this secret, and the secret cannot be stored in a cookie. This is because the browser would add it automatically to every request sent to the web application, just like the session cookie. Although every request can potentially be a forged one, it suffices to protect only those requests causing a state change on the web server. As previously mentioned, data query requests are less critical because the attacker cannot access the data included in the response. However, you may want to protect them against CSRF as well, should such queries create a denial of service risk due to high processing load on the target server. As a first step, review your application and determine which operations require CSRF prevention. You'll need to consider that a website having the ability to link a user directly into your application may be a desirable feature in certain cases, and that CSRF prevention will also affect these legitimate cross-domain requests. Determining whether a form in your web application is vulnerable to CSRF is simple. You only need to look at the form element HTML source. If the form consists of user input fields and does not contain fields with a secret value predefined by the server, then a request can be forged. As an alternative to inspecting the HTML form code, you can use web proxy tools such as Burb, Charles, or WebScarab to inspect which fields are sent to the server during a form transmission. If unpredictable values are not present, the attacker can embed a forged request in another website. This slide shows an example form. Imagine this is a banking website and that the form transmits the recipient account number and wire transfer amount. The form authentication is adopted from the session context determined with a session cookie. At a glance, you can tell this form is vulnerable to CSRF because attackers can construct a similar form on their websites, resulting in a valid post request to bank.example.com. They would know the names and values of all the fields they need to transmit in the request. For the account number and amount, they could include any value they like. Using JavaScript, they could automatically transmit the form when the malicious web page is loaded. Lastly, they must lure people to this web page and hope they're logged in to bank.example.com at the same time. Let's talk about how to fix CSRF in your web application. In most cases, you should be able to leverage an existing library or framework offering the necessary CSRF protection for your application. Nevertheless, it's important to understand how and under which conditions these prevention mechanisms work. The most common CSRF protection approach is to include a hidden token field into the form. The server presets a field value unpredictable by any attacker. A user form submission sends the token to the server unchanged, and the server only processes the request if the expected token is included. To do so, it must keep track of the tokens currently used in each user session. Since an attacker cannot predict the token value, it's impossible for him to forge an acceptable request to the server. Using unpredictable tokens implies that you don't use the same token in different user sessions. You must not assign token values in a deterministic manner, such as incremental counting, or choose them from a small value range. Generally, both GET and POST requests can transmit CSRF tokens. GET requests can only send tokens as URL parameters. However, POST requests allow sending the token in the body of the HTTP message. This has some security implications because URL parameters are at risk of being leaked at several locations. For example, the browser history, proxy, and web server log files record previously requested URL parameters. In addition, if your web page includes content from another server, the HTTP referrer header sends the URL parameter to this server. Similarly, if a link to a web page on another server is present, it sends the referrer header to this server if the user clicks on the link. If the token is a nonce and only valid for a single request, leaking the token after its usage is not a problem. Hence, if you need to protect GET requests against CSRF, you should generate a new token value for every request. Using the same token throughout the entire session is insecure due to the risk of leaking the URL parameter. CSRF prevention becomes simpler if your web applications follow the HTTP specifications for GET and HEAD requests. Though considered safe data retrieval methods, you must not use GET and HEAD requests to change any state on the server. By adhering to this specification, GET and HEAD requests are useless for CSRF attacks. Remember, due to the same origin policy, data returned in the response cannot be directly accessed by the malicious web page and is useless to the attacker. If POST requests initiate all state-changing operations, then only these requests require protection against request forgery. By sending the token as a POST parameter in the message body, we avoid leakage via the URL. Consequently, we do not need to generate a new token for every request. Generating one unpredictable token for each user session and using this token to protect all POST requests is sufficient. Unfortunately, many existing web applications do not adhere to the HTTP specification and use GET requests to trigger server state changes. Some web frameworks pull values out of GET and POST requests interchangeably, so the developer can't tell whether the parameter values sent were in the URL or the message body. Hence, several changes to the implementation and the configuration of the framework may be required to restrict state-changing requests to the POST method. As previously mentioned, you usually do not need to implement your own CSRF protection mechanism from scratch. Some web server implementations, such as Tomcat, have built-in deployable CSRF prevention functionality. Other web development frameworks offer simple ways to implement CSRF tokens. For example, ASP.NET implements the ViewState mechanism, which tracks user actions across different pages of the web application. By configuring the optional ViewStateUserKey variable with a secret value, the ViewState mechanism offers CSRF prevention as an additional feature. CSRF prevention-specific frameworks also exist, such as the CSRF Guard project driven by OWASP. Implementing any of these existing mechanisms ensures that your application is using the most well-tested fixes for your application, with a minimum amount of required effort. If you need to implement the CSRF token mechanism yourself, you must track valid tokens separately for every session. If token storage is a burden and you've already generated strong random session identifiers, the token can be calculated as a cryptographic hash value of the session identifier. Hence, the CSRF token can be validated by hashing the session identifier again and comparing it with the token value. You must not include the clear text session identifier as a token in the web page, because this would allow JavaScript to read it. Remember, protecting the session ID against JavaScript access is an essential mitigation against session hijacking via cross-site scripting. If you want to use hashed session IDs as CSRF tokens, ensure that the frequent calculation of hash values do not cause unacceptable computational overhead at the server. Token-based protection relies on the same origin policy that inhibits JavaScript in the malicious web page from reading any web content sent by the target server. Sometimes you may want to relieve the same origin policy by overwriting the document.domain property of the web page, or by setting the access control allow origin HTTP header in the server responses. In these cases, you must ensure that attackers cannot upload malicious content to any server in the same domain. Otherwise, the attacker can use JavaScript to read the web page content and extract the CSRF token. If you decide to use a token-based CSRF prevention mechanism, you must ensure that no cross-site scripting vulnerabilities exist that would allow attackers to access the CSRF tokens. This slide explains why this can happen. Since CSRF tokens appear in the HTML page, they are accessible by JavaScript and other scripting languages embedded in the same web page. The same origin policy prevents script access across domains. If an XSS vulnerability exists in your web application, an attacker can inject malicious script into your web page that reads the CSRF token and includes it in a subsequent forged request. When this occurs, the CSRF token can no longer aid in identifying legitimate user-initiated requests at the server. Reflected and DOM-based XSS vulnerabilities are particularly dangerous, as they're easily exploitable by a single forged request embedded in an external website. There are alternatives to token-based CSRF prevention. For example, when sending a state-changing request, you can prompt the user to re-enter his password or provide an unpredictable transaction number. The attacker cannot forge a valid request because he doesn't know this information. This is an easy way to mitigate existing cross-site request vulnerabilities, especially since few critical requests require protection, and re-authentication is acceptable from a usability point of view. Another alternative to token-based protection are CAPTCHAs. CAPTCHAs are small tasks requiring user solution before the web application can execute a critical action. Typical examples are images with random, difficult-to-read character sequences, which the user must decode and enter into a form field. The intended purpose of CAPTCHAs is to ensure that a human user sent a request and not an automated tool. A CSRF attacker cannot see the CAPTCHA, which makes solving it manually impossible. Randomized or encrypted URLs may also help defend against CSRF attacks. In this case, a string that varies among sessions replaces part of the original URL, with the resulting URL becoming invalid across sessions. Many web application firewalls offer this mechanism. However, there is a disadvantage. Randomized or encrypted URLs are unstable and cannot be bookmarked. Now that we've discussed CSRF at length, you may have realized that the entire web is vulnerable to CSRF by default. Links on one website referring to other websites are an essential web property. External web servers often source page content such as advertisements, videos, or maps. And if the external servers prevented cross-site requests, these legitimate use cases would no longer work. Google, for example, allows cross-site requests to its search engine. Therefore, any website can include Google search results. With the search engine being a public interface, you may believe this does not carry side effects. However, if you allow Google to record your search history to adapt future search results, cross-site requests may spoil the history. This could allow other websites to influence which results Google shows you in the future. Similarly, Google allows other websites to add bookmarks to registered users' bookmark lists. Here again, the user needs to be logged in to Google while browsing to the other website. While Google believes that such cross-site requests are a nice feature, it also understands that a cross-site request that changes a user's Gmail account preferences would be a problem. Therefore, Gmail preference requests are protected using CSRF tokens to ensure that they cannot be sent from any other website. Like Google, you will need to review the functions of your web application and determine which may result in a critical state change and require protection against CSRF. For functions with minor side effects, you may decide to allow cross-site requests for legitimate use cases. Now that we've talked about effective CSRF prevention practices, let's have a look at ineffective measures which may appear to be good CSRF prevention solutions. For example, you may think HTTP referrer header checking suffices when distinguishing between requests coming from your own website and those from external sites. The browser automatically adds the HTTP referrer header and contains the URL of the web page from which the request originated. Since requests issued from your website are assumed trustworthy, you could implement a filter that rejects requests from any other website. There are two reasons why HTTP referrer header-based filtering is unreliable. The first being that the HTTP referrer header is not always present. Some users may have privacy-enhancing proxy tools enabled that strip out referrer information emitted by their browser. So, if a web server denies requests missing the HTTP referrer header, the website will not work for these users. On the other hand, if requests without an HTTP referrer header are accepted, the website is unprotected against CSRF attempts originating from outside the browser. For example, forged requests can be embedded in an instant message, an email, or a PDF document, none of which are likely to include an HTTP referrer header. The second reason why HTTP referrer header-based filtering is unreliable is that the URL transmitted in the HTTP referrer header is not necessarily correct. Bugs in browsers and browser plugins can permit the attacker to forge HTTP headers as part of the attacker-generated request. The attacker could then forge the referral header in order to get past your HTTP referrer URL check. Another ineffective measure is adding a step to the workflow that asks the user for confirmation before the server processes a critical transaction, such as a wire transfer. Though this change breaks the original exploit, it does not protect against CSRF when the confirmation step involves a predictable request. The attacker would only need to send the confirmation request instead of, or in addition to, the original forged request. In order to turn the confirmation step into an effective countermeasure against CSRF, the corresponding request must be unpredictable for the attacker. As previously mentioned, you can make the request unpredictable through use of secret tokens, CAPTCHAs, secret transaction numbers, or by simply asking the users to enter their passwords. Let's summarize what we've learned during this course. Cross-site request forgery is a very dangerous type of attack that allows an attacker to remotely control the browsers of legitimate users of your web application. As such, requests received in the context of valid user sessions may actually be forged and emitted without the consent of the victim. Although you may argue that CSRF primarily targets the user, with user imprudence being the primary cause, successful attacks can affect your business. Tricked users will refuse responsibility for forged transactions that occurred without their knowledge, and evil users could attempt to exploit this situation and deny actions that they actually committed. After all, it is your application which does not provide user action non-repudiation. To protect against CSRF, you should review your application and verify that only POST requests change state on the server. GET and HEAD requests should be safe, and you should attempt to leverage existing frameworks implementing token-based CSRF prevention mechanisms before adding your own protection methods. Lastly, don't forget to address any XSS vulnerability in your application, which may render the CSRF prevention mechanism ineffective. Don't feel safe just because your application uses plugins, such as Flash or Ajax, or because your application is a web service instead of a typical website. None of these technologies is immune to CSRF, meaning, again, you need to check if critical, state-changing operations can be triggered using predictable requests. For further reading, we recommend the CSRF pages at the OWASP website and the references mentioned therein. Some additional useful resources are listed below.